Hello everyone. Good morning, Beijing. It's a pleasure being here, and it's really cool to see so many people coming to this conference to meet other Flink users, other people of the community, to listen to the talks, to exchange ideas, and yeah, it's pretty mind blowing to see so many people. I'm very happy to be here. Thank you very much. Okay, so. My talk today is called Stateful Functions, Building General Purpose Applications on Apache Flink. What does that mean? Haven't we always been building applications on Apache Flink? So yeah, today I would like to talk a little bit about how do we actually extend what Flink is from maybe a streaming system for data analytics, for real-time data processing, to something that can become a building block for an application infrastructure with which we build microservices, web services, and so on. This is it's a very early project in the Flink community, so we're basically sharing the beginnings of a new project that I think will take us on a new long journey to see how far we can actually take Flink and stream processing. Okay. I have some problems with the clicker here. Can we advance this slide? Here we go. Okay. Quickly before diving into the new stuff that we're doing in Flink, I would just like to take 2 minutes and look a little bit of what we have been working on in 2019 in the Flink community. And 2019 has really been a pretty big year for Flink. We've actually heard it before. Jeff, the CTO, mentioned it in his speech briefly already. In 2019, we actually saw, I think it's actually true, close to 1 million lines of code going into Flink. We saw the community more than double, actually, in many ways. And 2019 saw a lot of work on very many features. I've picked just a few ones to put on this slide here. To show you what we have been working on, and there's many interesting features. A lot of them around streaming analytics. So 2019, the features really helped us to go forward in the idea that the vision that we have in Flink in turning it into a unified system for batch and stream processing. And if you're familiar with Flink, if you're following the community a little bit, you actually know that Flink started out originally as a streaming batch system. It turned so we focused it into a streaming system, and now we're actually trying to turn it into really a very deeply integrated unified system. In 2019. Our work was contributing a lot to those trends. So starting out in Flink 1.9, we reached a stack that is shown on the left here. Added a new SQL engine. The Blink engine that was contributed by Alibaba. We finished the batch streaming unification on the SQL layer, and the next steps are really to take the same unification also to the data stream layer and really completely blend the boundaries between batch and stream processing. So the way I like to think about stream processing is that stateful stream processing, what Apache Flink encapsulates in its core, is really the foundation for a lot of different types of use cases and applications. There's the core. There's just the core stateful stream processing. You have streams, you have your state, you have time, and you're building near real-time data processing with that. On the other side, and this is what we're focusing on this year very much, is streaming analytics built with SQL streaming and batch SQL. Abstractions that take more analytical concepts, tables, declarative languages, and so on. And on the other side of the spectrum is what I want to talk about today. So, not Flink for actually data analytics and data processing, but Flink for what I think you can think of as event-driven applications. So yeah, while 2019 had a very strong focus on streaming analytics, I'd like to, and we're going to hear a lot more about this in the follow-up talks. I'd like to throw in a little bit from the complete other end of the spectrum, like a new kind of a new frontier for Flink that we're exploring. So let's look at what it takes to build applications with stream processing. And why are we even interested in talking about building stream processing applications with Flink? And I think if you look at how stream processing and applications how they go together at the moment, I think you can see that stream processing has very much become the connecting piece between data processing and online applications. So very many of the Flink use cases that we see, be that real-time recommendations or fraud detections, we can see that stream processing is really the piece that connects the analytical side of the application, that gathers the data, that runs the machine learning, that computes the statistics and so on, and then makes that accessible in real time to the applications to then show a search ranking, classify a payment as valid or as fraudulent. And the question we've been asking ourselves is how much can we actually get these two areas even further together? We see stream processing is supplying the data to the application, but then the applications actually themselves, they're still very, very separate units, even though they share a lot of the same characteristics as stream processing. They're also event driven in many ways. They're also really dealing with very high request rates. They're stateful. They need to do bookkeeping. So what is actually keeping these two things still apart? Why can't both of these things basically become the same thing under stream processing? We're just thinking about reacting to events in real time, and that was the question we were asking ourselves when we started with that, and then we went a little bit through the information we had on our Flink users. We went through the mailing lists and tried to figure out what are Flink users using Flink with when they're building real-time applications. They're using Flink for the data processing, but where are they making use of the data then in the end? And we found a lot of different technologies that were being used. I just picked a few here that probably most of you will know. There are very well-known application frameworks or application technologies being used today. And we're trying to also dig through through the technology trends and see what is happening. And the overwhelming trend we found is that while all of these frameworks are really popular, there were a few that were really surging in popularity. That were more and more people were trying to move their application onto these types of technologies, and those were the serverless functions in some sense. So the logos on the right are all functions as a service technologies. You may know Azure Functions, Amazon Lambda, and so on. And they're not. I don't want to talk about these technologies in particular, but they stand for a common type of of infrastructure, which is like serverless functions as a service. So that was a point where we thought, okay, this is interesting. So we see Flink being used for the computation, for the data processing, computing the real-time statistics, and then users are they're loading that into some other storage, and they're running their applications in a separate system, and they really like to build it on something like functions as a service. So what is the core of these frameworks, these serverless function frameworks? And yeah, as the name indicates, the core is this very simple piece. The core is this one event-driven function, and that got us thinking, because there's an event-driven function that is also something that stream processing actually has. If you think about Flink and writing a Flink application, most of the time, what you're actually doing is you're writing functions. You're writing a map function. You're writing a window function. You're writing a process function. You're writing a UDF in a table in a table or a SQL program. So there seem to be quite a few, in fact, quite a few overlapping pieces, quite a lot of technological similarities. So we tried to look at this a little closer. Why are these actually very popular? And the main thing why we saw users really liking these kind of functions was their, first of all, their most important property, the scalability. So they can parallelize pretty much infinitely, endlessly. But not only that, I mean, a framework like Flink and other frameworks can also parallelize. You can also spawn more instances. One really interesting property was the fact that this massive elasticity that these provided, it gave them a way to that each individual function has an extremely small footprint. It really only needs to run when data is coming, and when nothing is coming, it goes away. It doesn't occupy any resources. It makes it extremely efficient and cheap and lightweight. So that was really good. But there was also a downside to the whole thing, and that is when you're trying to build slightly more complex applications on this kind of systems, you're also pretty quickly running into some issues. So let's again look at we have a certain amount of state that we need to keep. We have, let's say, an application that is an e-commerce platform. And we're trying to build our checkout process or our shopping carts and so on functions as a service. What do we have to do? We do have to keep our inventory and our shopping carts somewhere, typically in a database. And then things, you can make this work, but you're starting to lose a little bit this nice serverless experience that you get in the simple case here, where you have this nice elasticity. You don't need to worry about anything. As soon as you throw the database into the mix, things actually become not as seamless or not as serverless as you like them to be anymore. There's many things you have to deal with. State consistency being maybe the most obvious one, but also just they're very mundane things you struggle with in these setups, like connection pooling, connection management. Somebody has to also manage and scale the database. So kind of the serverless story starts to break when you involve application state. And I think this is a topic that's being discussed quite a lot. If you actually search on many search engines for like problems with serverless functions, state management usually comes up as one of the top ones. And I just collected a few random opinions from the internet that I think actually say this pretty well. That there's we've made some really good advance in the area of orchestrating stateless applications, but we still have a lot of trouble actually orchestrating stateful applications and making the experience of those really nice. So there's so much work being put into systems like Kubernetes these days that help with this orchestration, but there's somehow a whole side of the problem that that all these systems have largely ignored so far. State being one of them, but I think if you try to build something slightly more complicated, you can see that there's actually other things as well that you struggle with. And one more thing that I found as one of the biggest problems there was actually how do you compose more complex applications from an individual set of functions. So, and then if we actually take a step back from this, we're coming from the background of Flink and stream processing, so we're looking at technologies that are event-driven, and we're looking at something that is event-driven functions, but that lacks composability and that has problems with state management. And composability and state management, isn't that kind of what we've been talking for 4 years in the areas of stream processing? That is kind of exactly what what our, let's say, daily bread and butter has been, like trying to make that part very easy, trying to be able to compose event-driven logic into complex applications, trying to make it out of the box work very well with stateful applications, trying to offer very powerful and yet very simple building blocks to build, consistent state and putting this all together. So there seems to be, very very clearly something that stream processing has worked on in the past years that is kind of missing in the serverless space. And at the same time, there's something in the in the functions as a service space that is clearly missing in the stream processing side. Otherwise, why is not everybody just using stream processing to use their to run their applications and their work? So there's some really good properties that both of these different types of technologies have brought. On the stream processing side, I just listed three properties here that I think are important in that aspect. That is the composability, the very sophisticated and very efficient state management, and also the performance that that stream processing gives you. The ability, if a stream processor is running, it processes events with very high performance, with very low latency. And at the same time, there's also some properties that we really like on the functions of the service side. So just the simplicity of having arbitrary functions that that basically do not need to only emit events and then they flow downstream to some other functions in your streaming data flow, but they basically can do whatever they want. And this really lightweight resource model that brings you this idea of you only need to pay for what you use. You don't need to have an entire cluster running on standby that you might not even be using at the moment. So is there some way that we can get some of these properties combined, that we can take the state management, the composability, the generality, the lightweight resource management, and try to find a way to combine them into one framework? And that is exactly the idea or the premise of the Stateful Functions project. So Stateful Functions is a new project that we've started a few months ago. We've announced it for the first time a few weeks ago. We made it public with the first version of the code, a website with examples and so on. You can currently find it under statefun.io if you want to check it out. And the idea is exactly what I talked about before, having both the ideas from stateful stream processings and the serverless application space to build a new framework to build applications in a different way than we used to do that before. I quickly want to mention that it is. I'm going to talk a bit more about this towards the end. At the moment, it is a standalone project that we're contributing to Apache Flink. So similar as last year, it was announced that Blink would be open sourced, and then over the next year contributed to Apache Flink. We've open sourced this stateful function projects, and we're at the moment contributing it to Apache Flink. So it is standalone for now. Probably if you check back in a month, it will be part of Flink already. So what is the core idea of stateful functions? What does it give you, and where is it different from what Flink does or what serverless functions do? I would try to explain what the core ideas of this project are, maybe with this picture. So at the core of stateful functions are stateful functions. So the project does not have an overly creative name. The name is really just what it really is. It's a set of functions with state, and from those you compose applications together. For those of you who have worked with actor frameworks before, there's some similarities to that, but also some very important differences that I'll go through next. So the first part of a stateful function application is always somehow this application has to get input, somehow it has to react to something. And because we think this idea of stream processing, that there's a well-defined way for events to enter the system, that is really a good idea. So we wanted to keep that. If you build a stateful function application, what you develop is you first of all define a set of so-called ingresses, which are sources of events in your application. And these can be these can be message queues like for example like Kafka or RocketMQ or Pulsar, Kinesis, Pravega. All the different systems that feed your streams and events, but we really want to define this, for beyond the pure stream event space. So we're also working on adding just simple HTTP servers as event ingresses that give you an event for every request. The next part is really the core of the application. It's a set of functions that you compose, and the idea here really is that you do a very, very fine-grained modeling of your functions. So you're not actually saying I want basically one big handler for my request that does the overall logic in one big monolithic unit, but think more as microservices, maybe even nano services or so. So you compose it into extremely fine-grained individual functional units. The biggest, or the very important thing that is very clearly inherited from stream processing is that all these functions have local state, right? That is very similar as in Flink in an even more generic way here. Every function just has almost a local database embedded that is always consistent. So you're not actually talking to any remote storage. You're really a self-contained stateful unit. What is very different compared to vanilla Flink is that we've actually come up with a model where every function can arbitrarily talk to every other function. So very different from Flink, where what you do is defining a data stream program of functions that send events to other functions in what has to be a directed acyclic graph. In this case, you just define functions and they can message each other completely arbitrarily. So you don't have to predefine a topology. You don't have to make sure that the events flow in an acyclic way. You can pretty much send messages however you want, very much like in a microservice or in an actor kind of setup. And I think that solved one of the biggest problems that we saw that people had when they were developing applications and they didn't want to build them on stream processing, because the streaming data flow way of both thinking and constraining the communication between the functions often just proved to be a deal breaker for developing many applications. So in that case, we relaxed that, just completely arbitrary messaging between functions. What we still preserve, though, is that while the functions message each other arbitrarily, we manage to keep the state and the messaging completely consistent together with each other. Similar as in stream processing, you send events downstream, you update states, but with the help of the exactly once fault tolerance mechanism, you're guaranteed to always get correct state, correct results. We wanted to do something similar here because we really found that this simplifies application development a lot, because that actually means you no longer have to think about duplicate requests, events in state overriding each other, messages getting lost, retrying, having to worry about the differences in semantics. Something that we also really clearly liked from stream processing and brought into this mix is the idea of not requiring a database, keeping the infrastructure simple, rather than having a key value store in the background that backs up all your state. The system is responsible for keeping the state by itself and take snapshots to the distributed storage. For those of you who have written Flink applications before, which probably are most of you, this is something that you're probably very familiar with. And then the final piece is responding to the outside world. We also felt you can make this much more consistent if you create a well-defined path, and that is the Egress API in this framework. So while every function can, of course, make arbitrary RPC calls and just interact with the outside world however it wants, if you use the Egress API to talk to the outside world, you're able to get better consistency. There's one more interesting aspect here that I would like to talk about, because that is quite different from how, for example, common actor systems work, or how you think about things often in the microservices world, and that is the notion of logical and virtual instances. So the way we would encourage you to build an application in the stateful function system is to go and create many functions, model it in an extremely fine-grained manner. So let's say you're building an e-commerce platform. We would suggest that you don't create one function to handle users, one to handle inventory, but the idea is to create a logical virtual function for each user, for each item in the inventory, for each shopping cart. And these virtual instances, you'd probably have billions or even trillions of them. And most of the time, those items would actually, they wouldn't really be active. They wouldn't really be doing something, because a user only comes once every few days. Some items might actually be rarely used, so they're mostly inactive. So the semantics we wanted to give these functions is the semantic of like logical virtual instances. If you've heard about virtual stateful actors, there's some similarities to that kind of technology. So what does that mean? It means that from all the function instances that you create in the system, not all of them have to be in memory at the same time, but they can be swapped out to disk, almost like virtual memory. And if we then come to the point that one function wants to send an event to another function, then what may have to happen is that that function isn't actually in memory, but by the time you send the message, that function is actually loaded into memory, another one might be evicted, and then you can actually go ahead and invoke that message. So that is, I think, a very big difference from how you think in classical actor systems, but it gives you a lot of flexibility, a lot of very nice tools, because you can really think in a very fine-grained manner about all your entities in the system. You don't need to worry about creating them, destroying them, deleting them. They just, it's just like you have a very large memory space, and then, like with virtual memory, objects go in and out of that memory space. So let me give you an example of the kind of applications that we really would like to make possible with this framework. And we have to, I have to say that it's an early stage project. It is very new, so some of these things work smoothly right now. Some of these things still need some improvement. But you can already build quite interesting and quite sophisticated applications. So one of the examples that is actually in the system, or in the project, if you go to the website and download the code, is this example, the example of a ride-sharing app. Think of something like Didi or Uber or Lyft, where you have passengers and you have drivers, and passengers hail cars and drivers pick up the passengers. And I think I have to apologize to the people from Didi and from Lyft that are in the room here. Of course, your business is a lot more complicated than this slide, but for the sake of making a simple example here, let's just pretend it would be as simple as that. So what you can see in this example is that we have different types of functions that we want to create. We have functions representing drivers, some functions representing passengers, and some functions representing ongoing rides. And as I mentioned before, you would actually go and try to model this in a very fine-grained manner. So every passenger would be its own function, every driver would be its own function. And when you start with a passenger, receiving or sending an event that they would like to to join a ride, then the passenger would message the ride function, which in turn would contact the geo-index and the drivers and find out what driver is in the vicinity, talk to many drivers, decide which one would be the driver to take the ride, and then communicate that back to the passengers. So you can see there's a lot of interaction between different functions, different updates of state, and types of communication that you cannot quite do with Flink these days. So yeah, this is the kind of applications that we really want to make possible with this framework, like really more general purpose applications on top of Flink. Maybe very quickly, one bit of detail on how do we actually do this on top of Apache Flink. So conceptually, what stateful functions give you is like a Flink workflow that has 3 steps. Events go in the ingress, then you have functions that just arbitrarily talk with each other, and then you have an egress for the data. The way that this runs on Flink is actually quite different than a normal Flink program. So the way stateful function works is that there's a single Flink program that acts as an interpreter of the program. So we do not take all these functions and we try to compile a complex data flow out of them, but there's a single Flink program that loads these functions and then basically acts as the state and messaging fabric for these functions. You can almost think of Flink as like the messaging database that loads the functions and then runs them. And I think that is a really exciting development. We're thinking of Flink here no longer as a stream processor that builds stacks, but it's like we're starting to think of it as like a streaming database that loads application logic and runs it. And one of the core things that we had to add to Apache Flink to make this possible is actually exactly once checkpointing of loops, right? Because that is, in some sense, how you build a general purpose interpreter. You build a loop, and then we basically run a distributed interpreter in a streaming loop. That is kind of the core of the project. You can find more details on how this works on the project website. So how do all of these pieces go together? So we have now this new thing. What is it meant to do? Is it meant to replace stream processing? Is it meant to replace functions as a service? I think neither nor. I think these pieces actually all go together very well and complement each other. So there's the idea of this stateful function type of applications, which are, I think, a good match for the very state-centric part of your application logic. And then there's still also the other two parts. They still exist, and they still have a very, very good place in this whole ecosystem. So we still have stream processing, which really excels at taking large amounts of data in real time and combining them and aggregating them and computing statistics over it. And we still have functions as a service, which are really good match for, here's a task that is compute intensive. It may take a while, but it's pretty self-contained. So just go and execute it. So I think all of these 3 things, you can find them in a big application architecture. You can find pieces that are state-centric, you can find pieces that aggregate data, aggregate information, and you can find parts that just do compute-intensive tasks in a self-contained manner. And let me try again with a ride-sharing example to show how these could possibly go together. So let's assume we have a few streams. Let's say updates from drivers, updates from passengers, and just maybe geolocation updates from drivers. You could, for example, have a stream processing application that combines updates from passengers and drivers to compute statistical models for, let's say, pricing, demand forecasting, the things that you need as input to matching drivers and passengers. Then you would have a stateful function piece that would deal with the coordination of those things, coordinating between drivers and passengers and locations. And then at the end of every ride, when you're done, maybe you want to do something that's a bit more intensive. You would want to render a map, you would create a PDF, and then send that to the passenger. So that's kind of a, let's say, more compute-intensive but self-contained task. And for those, you'd probably use you would probably use functions as a service. So all of these things that we talked about today, lambda functions, stream processing, and stateful functions. They all go together pretty nicely. As I mentioned before, it started out as an independent project. We're currently contributing it, and we're at the very last stage of the contribution. So the project has been accepted, and we're starting to merge the code into Flink. So if you look at the project in a few weeks, you'll probably find it part of Apache Flink as as a new API next to Data Stream API and Table API. And I'm almost at the end. I just want to give you one last pointer. The Stateful Function project is like the Flink project, initially a Java project. So it's it's part of the Java ecosystem. We write these applications in Java, but the next iteration of the project that we're already working on is very similar to opening up Flink for other languages, and that is adding support but for running different functions in other containers. So that you can actually use this not only with Java but also with, for example, Python or Go. And we're relying on very similar ideas as Apache Flink does there. And I think there's a talk later for example, how Flink does its integration with Python. Something very similar is happening here as well. And that's it. That's the end of my talk. If you think that this is an interesting project, I hope I managed to convince you a little bit that it is an interesting project. Then here are a few places that you can check out to learn more. There's the code repository, the website, and there are a few accounts where we're posting updates on the project. Thank you very much.